Welcome to Hartman Math. This is lesson 8.3, where we're going to find the inverse of a square matrix. So the definition of an inverse to a square matrix, and we can only find an inverse to a square matrix, but it is one such that where we multiply the two matrices, we get the identity matrix, which would be a square matrix with ones on the diagonal here, zeros everywhere else. That's the identity matrix, because if you multiply the identity matrix times any other same dimension matrix, you'll get that same dimension matrix. So if we had matrix B multiplied by I sub n, you would get matrix B. So the symbol, we kind of already know that for how we indicate inverse. So A is a matrix with the notation there, so that's the inverse of matrix A. So we can do it mechanically, especially pretty easy here for a 2x2 in a couple different ways. Here's the first way we're going to do it. We're going to use an augmented matrix. So what we do is we're going to write an augmented matrix for matrix A, where the right side, again we use the dotted line, but the right side is going to be the identity matrix. Like that. And then our goal is to use Gauss-Jordan elimination so that the left side becomes the identity matrix. And when we do that, the right side becomes the inverse matrix. So let's think about this. We can multiply the whole row here by a half, or we could do row operation number 3, multiply it by -2, and add it. Same thing here, same thing here, same thing here. And if we do that, that's our new row 1. So we've got our 1 here. Now we want to make this into a 0. So we're going to multiply by -5 and add to the 5. We do that column by column. So we've got our 1, we've got our 0. Next, we're going to look here. We're going to want to turn that into a 1. So we can multiply by a non-zero constant, operation number 2. Let's multiply everything, this whole row here, by -1/2. We're almost there. We've got 1s in the diagonal, we've got a 0 there. We need this to be a 0. So let's do row operation number 3. Let's multiply this by -1 and add it to the column above. So do that same all the way through. Multiply by -1 and add. We're going to get 1, 0, 0, 1, the identity matrix here. And the right side 3, -1, -5, 2. That is the inverse matrix to A. There it is. All right, go ahead and checkpoint. So pause the video here. Do the same thing. See what you get. All right. You should get this matrix, which we could pull out a factor as a scalar multiplier of 1/11, and then we get the matrix 3, -2, 4, 1. Right there is the inverse to B. So if you look at A and A inverse, and you look at B and B inverse, you might notice a pattern. You might notice and kind of see some of the same numbers, like a 1 and a 3 becomes a 3 and a 1. A -4 becomes a +4. A 2 becomes a -2. Now what about this? Well, that's part of it. In a 2x2 matrix, we can use that pattern. And that pattern looks like this. That the inverse matrix is 1 divided by the determinant of the original matrix A times, switch places here, so these two switch places, and then we go opposite sign for these two. Now why did it not look like that necessarily for the first example with A? It turned out that the determinant for matrix A was 1, so we didn't see that part to it. But for matrix B, the determinant was 11, So you see in the end we could pull this out as 1 over 11. So this is our second strategy for finding the inverse of a 2 by 2 is to use this pattern. So now let's use the formula to find the inverse of A. So we're going to begin with finding its determinant. 3 times 5 minus negative 4 times 1. We're going to get 19. So our inverse, and it's okay to leave it in this form. It's actually preferable not to multiply it in and get the fractions inside, but to keep it outside. We're going to get 1 over 19 times the matrix. Switch these two. Make that positive, make that negative. 1 over 19, 5, negative 1, 4, 3. There's our inverse. And we can use inverse matrices to solve an equation as a matrix equation, essentially solving a system of equations. So if we have some matrix equation, A, and that's going to be essentially a coefficient matrix, times X, a variable matrix, is equal to B, kind of call that the solution matrix. We can find X by doing the inverse of A times B. So remember, with matrix multiplication, order does matter. So it does need to be in that order. Let's take a look at what that looks like. Let's do it in a 2 by 2. So we're going to rewrite our system of equations into matrices, but not as an augmented matrix. It's essentially 3 separate matrices. A matrix for the coefficients. That's 2, negative 3, 3, 4. Multiplied by our variable matrix, X and Y stacked, and then equals our solution matrix, 10, negative 2. So that's how the matrix equation sets up. Remember from our matrix multiplication, if we were multiplying these, it would be first row matched up to first column, 2 times X, first and first, second, second, negative 3 times Y. That would equal this position right there. That's this equation. So that's how the matrix equation sets up. Now, what it says is XY, the variable matrix, which is what we're solving for, would equal the inverse of matrix A multiplied by matrix B. So we're going to need to find this inverse. Same way that we just did. Start with the determinant. 8 minus negative 9. So 1 over 17 times. Switch. Change to negative. Change to positive. There's our inverse matrix. So XY, the matrix, which has our X and our Y, is going to equal that times this. Now we can do the scalar multiplication now into either one of these, but not both. I would prefer just to do the multiply the two matrices first. Then we can do the scalar. So row by column, first and first, second and second, 4 times 10, 3 times negative 2, add those together, we get 34. On the bottom row, first and first, second and second, negative 30 and negative 4, that's negative 34. Now do the scalar multiplication, 1/17 times both of those. There we go. We got X is 2 and Y is negative 2, using inverse matrices. Example, the bomb. Let's solve a system of equations, a little bit larger one, a 3 by 3, but it really doesn't matter how big it is, using a graphing calculator. So what we're going to find out is all the work that we were doing in Chapter 7, at least the results of all of the equations, systems that we were solving, can be done with a graphing calculator, at least 95% of them. Let's check it out. So remember, we're going to need to set up two matrices, an A matrix and a B matrix. A is the coefficient on the left, B is the right side, 1, 1, 0. All right, let's set it up. Let's go into our matrix, second matrix right there. We want to edit number 1, which is matrix A. We now want that to be a 3 by 3 top row. 1, 2, 3. Row number 2, negative 2, negative 5, 3. Row number 3, 3, 7, negative 4. Always hit enter twice on the last one to make sure it's in there. Quit, second mode. Back into matrix, edit the B matrix. We now want that to be a 3 by 1. Right side was 1, 1, 0. Enter twice there. Quit. Now we're ready to perform the calculation. So access the matrix by choosing matrix. We want to choose matrix A. So A is now shown. We want A inverse times B. So over on the left, even though it doesn't really mean the same thing, x to the negative 1, in this context, the calculator knows that you would be referring to an inverse. And then we want to multiply that by matrix B. So again, into matrix, select in names B, and hit enter. There's our solution to our system. X is 7, Y is negative 3, Z is 0. Now, the only time that doesn't work is if our system has infinitely many or no solutions. And the reason that it doesn't work in terms of the inverses is in either of those cases, part of finding the inverse has to do with the determinant. What do you think the determinant is for a matrix, a square matrix that's going to lead to no solution or infinitely many? 0. When the determinant is 0, the matrix doesn't have an inverse. So if it doesn't have an inverse, this isn't going to work. So if you come up with an error and you try doing it, that could be the issue. It might be that the system has infinitely many or no solutions, and we need to find that by a different method. That's it for today. I'll see you next time.